impossible task, he came up with the equations that describe it, the theory of general relativity. Very complex, and that the acceleration and curvature are sort of interchanged. And he went out and made Eddington. You could go through and take an image of the sun being in front of a bunch of stars, and then waiting when the sun had moved on after the eclipse, and seeing if those stars had moved because of the curvature of space. And it turns out they did, and they moved just like his theory predicted. And so Einstein, when in sort of 1919, when this was realized, this is when Einstein became the person that the world knew as Einstein. And it's interesting, things we could not do with Newton's laws. And so it allowed us to solve cosmology for the first time. And when Einstein did this in 1916, 1917, his theory said the universe should be in motion. Now you say, well, yes, the universe is in motion. I've already shown you the universe is expanding. But he did not know that in 1916 and 17. And so he thought it must be a mistake. The universe looks static, makes the universe gravity push rather than pull. This is something he stuck to a little bit more complicated things on this diagram. And they kind of make sense. You'll note that that line is straight on 10 billion years old. And that's a problem because we know that the universe is infinite. It exists forever, and it goes on forever. On the other hand, if the universe is heavy, it will slow down, and it will end in what I like the universe that sort of comes to rest an infinite time in the future. They all start with a Big Bang, though, but the end is the question. As he told you, general relativity tells you that space, it will bend onto itself. Triangles will have more than 180 degrees. If the universe is light, space naturally bends away from itself, and triangles have less than 180 degrees. And so you end up with this interesting universe that a heavy universe, which has a beginning and end, is finite. It's finite in space and time. But I just want to show you, with these images of the James Webb Space Telescope taken last year, that you can actually see the curvature of space now directly with these telescopes very clearly. So this is a giant cluster of galaxies that act as a giant space magnifying glass. And you can see that distant galaxies here, these are all galaxies, some of them are the same galaxies, and the curvature of space. So you're directly seeing the curvature of space, and some of them get quite funny. In my PhD, we had brand new technology, and the technology were digital cameras and big computers that we could put on to telescopes in the case of the digital cameras. And my pitch was, we can go through and we can look into the distant past of the universe and measure how fast the universe is expanding now and a long time ago by looking at really distant objects. If I look at an object that's 5 billion light years in distance, then I'm looking back in the past 5 billion. Perfect trajectory where the universe is going to come to rest an infinite time in the future. That's the universe who learned how to use exploding stars called supernovae, giant thermonuclear bombs that rise and fall over the course of about 3 weeks, create most of the iron, for example, the Earth is made out of. And it turns out these things are 5 billion times brighter than our sun. And the sun gets old, it creates a white dwarf. And if our sun were, which is a tiny little star the size of the Earth, and if our sun were born as a binary, you'd get 2 white dwarfs that orbit each other. And it turns out those orbits, due to general relativity, creates... Now, one of the things we had to do was to use these new digital cameras that we're all very used to using today. And we would take huge amounts. And we did this by taking images before and then coming back 3 weeks later. And in this case, what you can see is an object went from nothing to something in the period of those 3 weeks. This object, 5 billion light years in the past, it exploded before the Earth was formed. So we really are looking back in the time as we do it. Now, it was quite a challenge because there were no software to do this. So my job as an astronomer was to write lots of software. Software to align the images, make them look the same. Each exploding star measures back in time how fast the universe is expanding. And you have the nearby objects on the left and the distant objects on the right. And, let's see if I get that again. And what you can see, not wanting to get into the spot where I'm going to cause feedback here, is the objects on the left are all consistent with any of the lines. But when we look back in the past, you can see we saw a surprise. We can see that those objects in 1999, that shows us actually trying to do this. So here we are in Chile, the driest place on the planet, Cerro Tololo. This is one of the co-founders from Chile, Nick Sunseth, here at the 4-meter telescope. And as the sun goes down, we get 6 nights a year on this telescope. That's more than anyone else on the planet gets on a telescope. So I'm sitting there watching the data, and my software is then going through it, trying to identify objects to figure out which ones are real and which ones are not. And time is of the essence, because less than 24 hours later, we're going to go to Hawaii to the Keck telescopes, the largest telescopes on the planet, to measure a spectrum. That is, we're going to spread the colors out in the rainbow and measure the redshift of these things. So it's a very intense experience to do. But as I said, you saw what we got. Oops. That we were 99.95% sure that the universe was speeding up from that data. Now 99.95 sounds pretty impressive. It's not quite enough for people involved in this experiment. So I think it's important to recognize the very large set of individuals who are involved in this discovery. So what's going on? Why is the universe accelerating? Why is it speeding up the expansion of the universe? The idea is that there is energy in every part of space that does not change. The universe was born with it. We don't know why, but it appears to be there, and it appears to be 70% of the universe right now. That is the way we can explain this with the physics we already know. Now, of course, we can go through and test that. If you have the universe full of this, you get a very different graph that you can go through and test. It turns out that the universe starts, but the universe was much smaller. It was denser. And so the gravity of attraction of all of us and all the atoms in the universe, that would have slowed the universe down for a while. But the universe is still getting bigger and bigger, but it's slowing down. Dark energy suddenly takes over, and then once it takes over, it's off to the races for the rest of the universe's life. So ultimately, our analysis, when you did everything in general relativity, said it's a mix of normal matter, that's the stuff in the laboratory, for understanding the universe. Because the physics in it is actually very simple. It is the physics of sound waves, because each of those bumps that you see there is actually a sound wave left over from the Big Bang. And we understand how sound waves travel. Let's just put it in terms of like throwing a rock into a pond, a wave in a pond. It turns out the wave action in a pond depends on what the pond's made out of. If it's made out of dark energy or dark matter, which I'll talk about in a second, it's a different set of waves than if it's just atoms or nothing. And so you can run the model and figure out what the waves look like, and then you can see what it looks like on a map of the sky. And so they were able to do that. I'm going to show you what the actual diagram looks like from the paper. This is a map of sound waves that have been measured in the universe, okay? And so, it's like this. You're very happy. And so what does that line say about the universe? Well, it tells you a couple of things. The first thing it tells you is the universe is not just made out of the atoms you and I are used to. There's something else we call dark matter that we've always thought existed, because wherever we look in the universe, we see more gravity than we see atoms. And that ratio matter out there, and it may well be an undiscovered particle. That's what we're looking for example, at CERN right now and other places. But it's a very specific type of particle that only interacts through gravity. Now, the other measurement we can make that is more important for dark energy is the sound waves have a certain size. And as I told you, the space is curved depending on whether or not, how much stuff. Indeed, it has 100% of the amount of stuff it needs to be just right. So it has not a little bit of stuff, not a lot, too much stuff, it's just in between. Now, that is a very percent of with the supernovae and also the cosmic microwave background kind of tell you that we needed this 70% mystery matter. And it turns out this experiment went a really weird way, but 95% of that stuff is stuff we do not see here on Earth. The only way we know an expansion rate of the universe. It turns out when my colleagues measure it in the nearby universe as accurately as we can, you get one answer. And when you measure it in the cosmic microwave background, those sound waves, it turns out you can measure what the Hubble constant is back then, and you can compare the two. And it turns out they disagree by about the James Webb Space Telescope, as I said, is making measurements of the sky. And one of the things that it's discovering in these amazing images are galaxies which are, their light is stretched so much that they're incredibly red. So you can see that really red galaxy where that arrow is at. So through something known as LIGO, we have been able to go through and see Einstein's prediction of gravitational waves, and we can see kind of space kind of wobbling when two black holes come together. And it turns out you can see that a lot. India is building a LIGO detector with the National Science Foundation in the United States. And there are lots of the image of black hole with radio telescopes spread across the globe. And this is sort of the shadow of the black hole showing up here. That black hole is 1 billion times bigger than our sun. And as we look back in time, we see only 1 billion years old. And it's really quite understand yet. So I would wait to understand what's going on. It could be black holes were born at the time of the Big Bang and are messing up the physics in some weird way, or something else. I just don't know. Now, often people ask me, yeah, understand energy. As I said, once it takes over, it just keeps making things get bigger and bigger and bigger. So the more space expands, the more dark energy push against gravity, and that creates even more space, which means the dark energy dominates even more. And so eventually the creation of it today is going to be traveling towards us. Space is expanding faster and faster, and the light will get stranded on the way here. So we will end up with a universe that is, unless dark energy for some reason suddenly disappears, for no reason we can think of, the universe will, at an ever-increasing rate, expand, fade away, leaving me as a cosmologist